copper oxide planes, as it has been discussed already today, are instrumental for the creation of the superconducting state, and electrons from these pairs actually form Cooper pairs as we increase hole doping, as shown by this very well-known phase diagram. It is also very well established that the D-wave pairing symmetry is realized in those systems, as seen here in the RPS data. So, as it seems that those copper oxide planes are very important for the creation of the superconducting state, people were also trying to analyze experimentally the superconducting features of a single copper oxide plane where when it is deposited on a substrate, and the schematic of such system is shown here in the left upper corner of the slide. I am also showing here an STM image from this paper from 2016, which shows that they have actually obtained such copper oxide plane in which copper and oxygen atoms are. So, as I said before, they have obtained those from this paper. We can see that people are able to obtain this copper oxide monolayer film on a substrate. And in the low temperature regime, this copper oxide monolayer film is superconducting. And interestingly, the STM conductance measurements show this characteristic U-shaped local density of states, which tells us that we are dealing with a fully gapped situation. So the superconducting gap is opened at the full extent of the Fermi surface. So this is not compatible with the D-wave pairing scenario, because in such case we wouldn't have it isn't possible to obtain these nodal lines, which are established for the case of the bulk copper-based compounds, in which the same copper oxide planes are stacked inside a bulk material. So those two contradictory results for the copper oxide monolayer and for the bulk copper-based compound for the two seemingly similar systems have raised some questions and gathered some interest. And in this theoretical paper, it has been proposed from 2018. It has been proposed that yes, indeed, we have similar building blocks which leads to superconductivity, which are those copper oxide planes. However, in the bulk compound and in the copper oxide monolayer, the electronic structure is slightly different. Namely, in the bulk compound, we have the 3D9 configuration of the copper atoms, which leads to an effective half-filled single band description, as shown here. Whereas for the case of the copper oxide monolayer, some of the charge flows through the interface and enters the substrate. Therefore, we are realizing a heavily hole overdoped situation. We are close to the 3D8 configuration, and the DFT calculations show that those two d orbitals of the copper become operative, and that leads to a two-band description of the system. So it has been proposed that in such situation, an S-wave superconducting dome can appear, and this group has analyzed an spin orbital exchange interaction induced superconductivity, and we were actually wondering if we can apply a previously known TJU model by extending it to a two-band form and reconstruct such S-wave superconducting dome in a heavily hole overdoped regime. This is the model that we have been using. So we have the kinetic energy term, which is obtained within the tight binding approximation. Of course, we have those electron hopping terms of proper values, which leads to the reconstruction of such electronic structure. And we have the kinetic exchange term, which plays the role of superconducting pairing, similarly as in the standard case of a TJU model, which in its single band variant has been previously applied to bulk cuprates. So this term essentially lowers down the energy of the system whenever a spin singlet electron pair is created on the neighboring atomic sites. So this, in a straightforward manner, leads to a real space pairing with superconducting gap amplitudes in the X and Y direction. And if those two are equal, we obtain extended S-wave superconducting pairing symmetry. If this anti-symmetric situation appears, we have a D-wave superconductor with the nodal lines which have been verified for the bulk cuprates. Of course, we have also the Coulomb propulsion term and the Hund's term. And since those Coulomb interactions may be significant, we have to take into account electron-electron interactions, and we have been doing that by using the diagrammatic expansion of the Guth-Hiller wave function, which goes beyond the normalized mean field theory. However, I'm not going to talk about the method since there is no time, and let's move to the results already. So for the case of the copper oxide monolayer film, for the two-band analog of this TJU model, we have obtained in the heavily Hall overdoped regime such superconducting dome, which is of extended S-wave symmetry. So it fulfills this requirement. And now one might ask why do we obtain this critical Hall doping value after which the superconductivity is created. So this value actually corresponds to a Lifshitz transition, after which the lower band becomes partially filled and the additional Fermi surface fields appear. So the Fermi surface topology changes from this one to that one after crossing the Lifshitz transition. And on this density of states plot, the Lifshitz transition corresponds to this point. So as we increase Hall doping, we decrease the Fermi level, and at some point we encounter this rapid increase of density of states. So this increase of density of states stabilizes superconductivity. High density of states works in favor of superconductivity, not only in the case of phonon-mediated pairing, also for other pairing mechanisms, as the one considered here. So that's why we obtain this critical value of Hall doping after which the dome is created. So for the sake of completeness, I'm also showing calculations within a single band TJU model for the bulk copper-based compounds. And here, as it is previously has been known that the D-wave superconducting dome appears, the Fermi surface looks like this, and the density of state looks like this. So moving in this weak to moderate Hall doping regime, we are actually in the regime of those density of states values. For the case of the bare band situation, of course, which can be changed due to electron-electron correlations, of course. So with that, we have reconstructed this schematic phase diagram in which we have this S-wave superconductor here in the form of an extended S-wave symmetry. However, it also is fully gapped since it is away from the nodal line, so it is in agreement with the experimental STM measurements. And this D-wave superconducting dome corresponds, of course, to this figure in the left bottom region of the slide. So now one might ask why we have this kind of pairing symmetry between those two situations. And according to our analysis, it is because of the relative position of the Fermi surface with respect to the nodal lines corresponding to a particular symmetry. So for the extended S-wave symmetry, the nodal lines form this squared shape. And as we can see from this figure, the Fermi surfaces are all away from those nodal lines. Therefore, those nodal lines, the symmetry factor won't be suppressing the superconducting gap at the Fermi surface, the superconducting gaps, yeah. So that's why the extended S-wave symmetry is realized, because the D-wave symmetry nodal lines goes like this, and they would suppress in those 8 points, they would suppress the superconducting gap at the Fermi surface. So energetically favorable is to choose the extended S-wave scenario. Here, for the case of bulk coprates, we have the Fermi surfaces which look like this, and on the whole extent of the Fermi surface, they are close to the nodal lines corresponding to the extended S-wave symmetry. Therefore, this proximity would suppress the superconducting gap at the Fermi level, at the Fermi surface, at its whole extent, and this is unfavorable energetically. That's why the system chooses to be a D-wave superconductor, where we have only those 4 points at which the superconducting gap is suppressed. However, it is not suppressed on the whole extent of the Fermi surface, and this is more favorable when it comes to stability of the superconducting state. So we have also analyzed the occupancy at those two orbitals, and we can see that we obtain this non-monotonicity in the occupation number for the x squared minus y squared orbital. So we have decreasing and then increasing number of electrons at this orbital as we take away electrons from the system, because with increasing doping electrons, there are less and less electrons in the system. And in spite of that, actually electrons in this upper orbital are their number is increasing. And the change of monotonicity appears at the Lifshitz transition. And it can be understood as an effect of interorbital Coulomb repulsion. And we can look at this within the simple Hartree-Fock picture, The corresponding terms are shown here. So we can see that from this Hamiltonian, there is an effective change of orbital energy level due to interorbital Coulomb propulsion. V is the interorbital Coulomb propulsion integral. And Nz is the occupation number of electrons in the other orbital. So as we pass through the Lifshitz transition, actually Nz is going down. So if Nz is going down, the whole dispersion relation moves down in energies, which correspond to the xy minus x squared minus y squared orbital. So if this whole dispersion relation goes down in energies, electrons fall onto this band, and more electrons are occupying this band. That's why this change of monotonicity at the Lifshitz transition appears, and a similar effect has been already verified for a different system, but there are some similarities, namely for the lanthanum aluminate nanofilms on the STO substrates, which is also a two-band system with a multi-band character with significant values of the Coulomb repulsion, in particular interorbital Coulomb propulsion. And at this transition, they have also obtained this, actually here experimentally, not theoretically, this change of monotonicity. However, here it was from increasing to decreasing. In our case, we have the reverse situation. And this is because here for LAO-STO, we have only electronic bands crossing electron-like bands crossing the Fermi level. In our case, we have also a hole-like band, and that's make the situation reverse. So instead of increase and decrease, we have a decrease and increase. Okay, and the last thing I would like to say, I hope I'm not too late still. So are the results for the case of this copper-based compound, for which superconductivity has been reported quite recently, actually, and it's quite unusual compound in the cuprate family because the distance between the apical oxygen and the copper oxide plane is relatively shorter, as shown here, with respect to the other cuprate representatives. So this leads to narrowed down octahedron in the crystal structure, as shown schematically here, which in turn leads to a different to a reverse situation when it comes to those two d orbitals. So this 3z squared minus r squared orbital is higher in energy than the x squared minus y squared, as shown here. And this is the reverse situation with respect to the one which we know from the previously known cuprates, which is shown schematically here. So the X-ray measurements also show that we are dealing with an extremely highly Hall overdose situation for this compound. And those two situations, those two things that I have been talking about, leads to a conclusion that this compound actually has a lot in common with the copper oxide monolayer film, which I have been discussing previously. And that's why we were interested in this compound also. And in this paper, theoretical paper from 2019, the authors have proposed tight binding approximation model, which approximates between the single band scenario, which corresponds to the previously known cuprates, and the two band scenario, which corresponds to this particular compound. And with this, we have applied also this TJU-based approach to this tight binding approximation, and we have obtained this two-dome structure in the very wide doping range, going from the weak to extremely heavily Hall overdosed situations. And this first superconducting dome is of D-wave symmetry. The second one is of S-wave symmetry, similarly as for the case of the copper oxide monolayer film. And also here we have obtained this change of monotonicity in the occupation number of this x squared minus y squared orbital, the orbital. So, okay, so I will not go into further details here since we are already running out of time. So let me go to the conclusions. So we have shown that the extended S-wave, so fully gapped superconducting state, is stable in this two-band analog of the TJU model, as applied to the description of the copper oxide planes, and the appearance of the paired state is due to the heavily is due to the fact that in the heavily Hall overdoped regime we have a rapid increase of the density of states at the Lifshitz transition, which is due to the fact that the bottom band is becoming partially filled, And these high values of the density of states in the bottom band are due to the fact that the bottom band is even more flat than the upper band. So its bandwidth is something about 1 electron volt. So this is, from this flatness, we obtain high value of the density of states. And now, because of the symmetry, of the gap symmetry is determined by the relative position of the Fermi surface and the nodal lines of the particular symmetry factor. And we have also applied the same approach to the recently discovered superconducting state for this barium-based, well, copper-based, but with barium bulk compound, and we have obtained this two-dome structure with S-wave and D-wave superconductivity. And at the end, I would like to only mention the financing agency, which is the National Science Center of Poland, and with that, I would like to thank you for your attention.